There is a place in our universe where the known laws of physics unravel, where gravity becomes so overwhelmingly powerful that not even light can escape its grasp, a region where time itself bends and distorts into something unrecognizable. This is not science fiction. This is the reality of black holes, the cosmos' most enigmatic and intimidating phenomena. For decades, they have captivated scientists, philosophers, and dreamers alike, representing the ultimate frontier of human understanding. But what if everything we thought we knew about black holes was only the surface? What if, deep within these cosmic monsters, lie structures and secrets so profound they challenge the very foundations of reality? Today, we're venturing beyond the event horizon to explore 25 hidden structures inside black holes. Theories so revolutionary, so startling, that most people have never even heard of them. We're talking about cosmic firewalls that incinerate anything that approaches, quantum fuzzballs that replace singularities with vibrating strings of energy, and white holes that might fountain matter into other universes. These aren't just wild speculations. They are serious scientific proposals emerging from the cutting edge of theoretical physics, born from the collision of quantum mechanics and general relativity. Each one offers a new way to see these celestial mysteries, not as destructive endpoints, but as dynamic, complex entities that may hold the keys to understanding the universe itself. This journey isn't just for physicists. It's for anyone who has ever looked up at the night sky and wondered what lies beyond our comprehension. It's about questioning what we accept as truth and daring to imagine what might be hidden in the heart of darkness. So prepare to have your mind stretched, your curiosity ignited, and your perception of reality transformed. We're about to dive deep into the unknown, exploring ideas that don't just redefine black holes. They redefine existence itself. The story of black holes doesn't begin with a flashy discovery, but with a quiet revolution in thought. It all started with Albert Einstein's monumental theory of general relativity in 1915, which reimagined gravity not as a force, but as a warp in the very fabric of space and time. Almost immediately, a German physicist named Karl Schwarzschild, while serving on the front lines during World War I, found a solution to Einstein's complex equations. His work described a point of such immense density that it created a region of space from which nothing, not even light, could return. This was the first mathematical glimpse of what we now call a black hole, though it was so strange and seemingly impossible that even Einstein doubted it could exist in the real universe. The next great leap forward came from a young Indian astrophysicist, Subrahmanyan Chandrasekhar, on a long sea voyage to England in the 1930s. He calculated that a dying star above a certain mass, now known as the Chandrasekhar limit, would not be able to support itself against its own gravity and would collapse indefinitely. This idea was fiercely debated at the time, but it planted the crucial seed that black holes weren't just mathematical oddities. They could be the natural end states of massive stars. It took decades for the scientific community to fully accept this radical notion. The term black hole itself wasn't even coined until 1967. By the visionary physicist John Wheeler, giving a name to the unimaginable and bringing this dark concept into the lexicon of science. For most of the 20th century, black holes remained purely theoretical beasts. The turning point came with the discovery of quasars in the 1960s, incredibly bright, distant objects that could only be powered by the immense gravitational energy of supermassive black holes. This was the first observational evidence that these cosmic predators were not only real but active and shaping the universe around them. The proof kept mounting. The detection of gravitational waves in 2015, from the collision of two black holes over 1 billion light-years away, was a monumental confirmation, allowing us to literally hear the ripples in space-time they created. And then, in 2019, the Event Horizon Telescope collaboration did the seemingly impossible. It presented humanity with the first direct image of a black hole's shadow, a fiery ring of light encircling the darkness at the heart of the galaxy Messier 87. This journey, from abstract equations to a tangible photograph, transforms black holes from science fiction into scientific fact. It's this rich history of relentless curiosity and brilliant deduction that sets the stage for the even wilder ideas we're about to explore. Theories that venture beyond what we can currently see and into the hidden heart of darkness itself. But what if that terrifying singularity, that point of infinite density, isn't the final word? What if, at the very center of a black hole, there's something else entirely? A structure that prevents the ultimate collapse and rewrites the destiny of these cosmic giants. This brings us to our first hidden structure, a concept born from the fiery marriage of quantum theory and gravity, the Planck star. Imagine the final moments of a massive star collapsing under its own weight. According to Einstein's general relativity, this collapse would continue unchecked, crushing all matter into an infinitely small, infinitely dense point, the singularity. But most physicists agree that this infinite result is really just a sign that the math has broken down, a signal that we're missing a crucial piece of the puzzle. That missing piece is quantum gravity, a theory that seeks to describe how gravity operates at the smallest possible scales. And one of the most fascinating proposals from this field is that the collapse doesn't create an infinite point, but instead is halted, creating a tiny, incredibly dense object no bigger than the Planck length. That's a millionth of a billionth of a billionth of a billionth of a centimeter. This is the Planck star. Unlike the silent, dead singularity, a Planck star is thought to be a dynamic, pulsating object. It's a remnant that has reached a state of maximum possible density allowed by the laws of quantum physics. And at that point, the repulsive force of quantum gravity becomes so powerful that it counteracts the immense pull of collapse. Think of it like compressing a spring. You can push it down, but eventually it pushes back with equal force. The Planck star is that cosmic spring, bouncing and oscillating at the heart of the darkness. This isn't just a wild guess. It emerges from a well-studied framework called loop quantum gravity, which suggests that spacetime itself is woven from tiny, discrete loops. At the extreme pressures inside a black hole, this granular nature of space-time puts a hard limit on compression. The existence of a Planck star would have staggering implications. For one, it would mean black holes are not eternal prisons. If the core is a bouncing ball of quantum energy, then the entire life cycle of a black hole could be dramatically different. Some models suggest that after absorbing matter for eons, a black hole might eventually rebound. This rebound wouldn't be fast. We're talking timescales longer than the current age of the universe for a typical black hole. But in this scenario, the black hole could potentially explode, transforming from an object that consumes everything into a fountain of new matter and energy, perhaps even giving birth to a new universe. This turns the classic notion of a black hole as a cosmic dead end completely on its head, reimagining it as a transient phase in the life of matter, a dormant seed waiting for its moment to bloom again into something new. But what if the Planck star isn't the only way to avoid the horrors of a singularity? What if the very idea of an event horizon, that point of no return, is itself an illusion? Our next hidden structure proposes exactly that, offering a radical alternative that reimagines black holes not as voids, but as some of the most exotic and stable objects in the universe. Welcome to the strange and counterintuitive world of the Gravistar. The term Gravistar is a portmanteau, blending the concepts of a gravitational vacuum star. The core idea is as elegant as it is bizarre. Instead of a black hole's empty space warping down to an infinitely dense point, a gravistar would be a celestial object with a defined structure. Picture it like a cosmic egg. Its shell would be made of an incredibly thin, super-dense form of matter, perhaps only a few centimeters thick but so compact that a single teaspoon could weigh more than a mountain. This shell is what we, from the outside, would mistake for an event horizon. It would bend light and trap matter almost identically, explaining why gravastars would be observationally almost indistinguishable from traditional black holes in many ways. But the crucial difference lies inside the shell. Instead of a crushing singularity, the interior of a gravistar would be a vast, hollow core filled with a mysterious substance known as dark energy. This is where the theory gets truly mind-bending. Dark energy is the same enigmatic force that astronomers believe is causing the expansion of our entire universe to accelerate. It has a strong negative pressure, effectively acting as a form of anti-gravity pushing spacetime apart. Inside a gravistar, this repulsive dark energy core would be in a perfect, stable balance with the immense inward pressure from the ultra-dense shell. The gravitational collapse is halted not by quantum bouncing, but by this exotic interior pushing back, preventing the formation of a singularity altogether. This elegant solution emerges from a sophisticated reworking of Einstein's equations of general relativity, specifically by incorporating the quantum energy of the vacuum. It shows that the math of our universe might permit these bizarre objects to exist. The implications of gravastars are profound. They would resolve many of the thorniest paradoxes associated with black holes. The information paradox, where information about what falls in seems to be lost forever, violating quantum mechanics, simply wouldn't arise because there is no singularity to destroy that information. The problems of infinite density and the breakdown of physical laws are also neatly sidestepped. If gravastars are real, they challenge the very definition of a black hole. They are not holes or voids at all, but rather incredibly dense, exotic stars. This opens up entirely new cosmological models, suggesting that the darkest objects in our sky might not be the destructive endpoints we fear, but rather stable, albeit utterly alien, structures that have found a new way to exist within the extreme laws of physics. But what if we've been picturing the inside of a black hole all wrong? What if it isn't a vast, empty space falling into a single point, but something far more textured, more complex, and alive with information? To find out, we need to turn to one of the most ambitious theories in all of physics, string theory, and its astonishing proposal for what truly lies within, the fuzzball. For decades, the accepted image was one of terrifying simplicity. Cross the event horizon and you enter a void, a region of warped space that funnels everything inexorably downward toward the central singularity, a place where the laws of physics cease to exist. String theory, however, paints a radically different and far more fascinating picture. It suggests that what we call a black hole is actually a gigantic, tangled ball of vibrating strings, a fuzzball. The name itself captures its essence. This isn't a smooth, empty spacetime. It's a fuzzy, vibrant, and incredibly dense structure that has no sharp boundary and, most importantly, no singularity at its center. The entire interior, from where the event horizon was thought to be all the way to the center, is completely filled with this complex web of strings. The event horizon isn't a special membrane you cross. It's simply the outer surface of this gigantic, pulsating ball of energy. This idea isn't just a whimsical alternative. It emerges as a direct solution to one of the most vexing problems in modern physics, the black hole information paradox. The paradox, famously highlighted by Stephen Hawking, asks a deceptively simple question. What happens to the information about an object that falls into a black hole? Quantum mechanics insists that information can never be truly destroyed. Yet the classical black hole model suggests it is irretrievably lost down the singularity, vanishing from our universe. The fuzzball model resolves this with breathtaking elegance. Because there is no singularity, there is no place for information to be destroyed. Instead, Every single bit of information about what has fallen in, every atom, every particle, every property, is meticulously stored in the precise vibrational patterns and intricate entanglement of the strings that make up the entire fuzzball. The information is never lost. It is simply encoded into the very fabric of the black hole's being. This leads to another profound insight about the nature of black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a measure of disorder or information content, and that this entropy is proportional to the surface area of the event horizon, not its volume. This was deeply puzzling. In every other system in the universe, entropy scales with volume. Why would a black hole be different? The fuzzball provides a stunningly natural explanation. The surface of the fuzzball is the event horizon, and it is on this two-dimensional surface that the information about the entire three-dimensional interior is holographically stored. The entropy is a surface property because that's where the data lives. The complex interior is a projection of that information. The fuzzball doesn't have entropy. It is entropy, made manifest as a physical object. So, instead of a cold, dark, and silent abyss, envision a cosmic knot humming with unimaginable energy. Picture a ball of strings, each one vibrating at a specific frequency, woven together into a complex tapestry that holds the story of everything it has ever consumed. It is a dynamic, information-rich entity, a universe of data packed into a tiny space. This vision transforms black holes from simplistic destroyers into the universe's ultimate libraries, each one a unique and detailed record of its own history, challenging us to see the cosmos not as a collection of empty spaces, but as a deeply interconnected network of information. Yet this elegant fuzzball solution, for all its brilliance, sparked an even more radical and terrifying idea. What if the conflict between quantum mechanics and general relativity doesn't resolve peacefully into a ball of strings, but instead erupts into a cataclysmic inferno? This line of thinking leads us to our fourth hidden structure, a concept so violent it fundamentally reshapes what it means to cross the point of no return, the black hole firewall. For nearly a century, a principle known as the equivalence principle has been a cornerstone of general relativity. It states, in simple terms, that if you were falling freely in a gravitational field, like plunging into a black hole, you wouldn't feel any immediate, dramatic effects as you crossed the event horizon. From your perspective, it would be a smooth, uneventful journey. You wouldn't suddenly see a sign saying, "Welcome to the abyss." This principle ensures that the laws of physics are consistent for all observers, whether they are floating in deep space or accelerating in a rocket. The event horizon was thought to be a mathematically smooth, albeit one-way, doorway. The firewall theory shatters this classical tranquility. It proposes that just inside the event horizon, there isn't empty space but a searing, blistering wall of unimaginably high-energy radiation. This isn't a metaphorical wall. It's a literal curtain of particles with energies so intense that any object, a spaceship, an atom, even a person, would be instantly vaporized into its most fundamental components upon contact. The theory emerged not from a desire to be dramatic, but from a desperate attempt to reconcile two conflicting truths about black holes. On one hand, quantum mechanics demands that information cannot be destroyed, suggesting that the information about what falls in must somehow be preserved or radiated back out, as in the fuzzball model. On the other hand, this very process of preserving information via Hawking radiation seems to require a drastic violation of the equivalence principle at the horizon. The core of the paradox is a quantum phenomenon called entanglement. Empty space isn't truly empty. It's a seething foam of virtual particle pairs constantly flickering in and out of existence. Normally, these pairs annihilate each other almost instantly. But at the event horizon, one particle can fall in while the other escapes, becoming the Hawking radiation that slowly evaporates the black hole. For this process to carry away information and preserve the laws of quantum mechanics, the two particles must be intricately entangled. However, calculations showed that this creates an impossible situation, a phenomenon called monogamy of entanglement, where the particle that fell in cannot also be entangled with the rest of the black hole's interior. To resolve this mathematical inconsistency, physicists Ahmed Almeri, Donald Marolf, Joe Polchinski, and James Sully found that the only escape was to break the entanglement at the horizon. And the energy released by severing these countless quantum connections would be astronomical, manifesting as a literal wall of fire. The implications of this idea are staggering and deeply controversial. A firewall means that the event horizon is not a smooth gateway but the ultimate cosmic kill zone. It suggests that the interior of a black hole, as classically imagined, might not even exist for an infalling observer because they would be destroyed before they could ever experience it. This doesn't just challenge a minor detail of black hole theory. It forces a direct confrontation between our two most successful descriptions of the universe. Either the equivalence principle of general relativity is wrong at the horizon, or our understanding of quantum mechanics and information is flawed. The firewall highlights a fundamental schism in physics, a glaring signpost that our current theories are incomplete, and that a deeper theory of quantum gravity is needed to tell us what truly happens at the edge of reality. It presents us with a universe that is far more violent and less forgiving than we ever imagined. Yet beyond the firewall's destructive fury lies another boundary, a second gateway hidden deep within the swirling darkness that promises an even stranger fate for anything that survives the initial plunge. We now venture into the complex heart of a rotating black hole, a region described by the elegant mathematics of physicist Roy Kerr, to encounter our fifth hidden structure, the inner horizon. If the event horizon is the main entrance to the abyss, the inner horizon is a secret inner sanctum. In the simplest black holes described by Schwarzschild's solution, there is only one horizon and a direct, one-way ticket to the central singularity. But the universe is dynamic, and most black holes are expected to spin, a legacy of the angular momentum from the star that collapsed to form them. This rotation twists the fabric of space-time around it, dragging everything into a swirling vortex and fundamentally altering the interior architecture. The Kerr solution to Einstein's equations reveals that a spinning black hole has not one, but two distinct horizons: the familiar outer event horizon and this new, inner Cauchy horizon. Crossing the outer horizon may be uneventful, but passing through the inner horizon is where the true weirdness begins. This inner boundary acts like a cosmic catch basin. While the outer horizon prevents anything from escaping the black hole, the inner horizon is a point where infalling matter and radiation, all following different paths through the warped spacetime, can theoretically pile up or converge. Imagine it as a place where all the light and debris that has ever fallen into the black hole over billions of years is focused into a single, searingly bright shell of energy. The tidal forces here, the difference in gravity between your head and your feet, would become infinite, shredding any complex structure into its most elementary particles. It is a region of unimaginable energy density, a crucible where physics is pushed to its absolute limit. However, this theoretical convergence may be its own undoing. Many physicists believe the inner horizon is fundamentally unstable. The very act of matter and energy piling up at this boundary could create a feedback loop of immense power, a sort of gravitational echo that rips through the black hole's interior. This instability might not just destroy the inner horizon. It could trigger a violent eruption, a catastrophic release of energy that effectively acts as a firewall from the inside out, obliterating anything approaching the center. In this scenario, the inner horizon becomes a natural, physical manifestation of the firewall paradox, a place where the classical equations of general relativity break down and scream for a quantum explanation. But there is another, even more speculative possibility for this mysterious boundary. Some interpretations of the complex mathematics suggest that passing through the inner horizon might not lead to annihilation, but to a gateway. Beyond this point, the equations allow for paths that could, in theory, lead out of the black hole entirely, not back into our own universe, but into a completely different one. Or perhaps even into a different time. The inner horizon could be the entrance to an Einstein-Rosen bridge, the throat of a wormhole, offering a passage through the cosmos that bypasses the dreaded singularity altogether. This transforms the black hole from a mere trap into a potential cosmic transit system, a hidden tunnel in the fabric of reality, with the inner horizon serving as its volatile and treacherous port of entry. It stands as a final frontier within the darkness, a membrane where the known laws of physics dissolve and the truly unknown begins. While the inner horizon presents a volatile gateway deep within a spinning black hole, the profound effects of rotation are not confined to the interior alone. Just outside the event horizon lies a region where the black hole's spin warps the very fabric of the cosmos into a cosmic whirlpool, a place where the universe itself is forced to move. This is the ergosphere, a structure that, while not hidden inside, is absolutely critical to understanding how black holes interact with and even power the universe around them. The ergosphere is a direct consequence of a black hole's rotation, described by Roy Kerr's solution to Einstein's equations. Imagine the event horizon as the ultimate point of no return, a spherical boundary. The ergosphere is a larger, flattened region that surrounds it, shaped like a squashed sphere or an oblate spheroid, bulging at the equator due to the centrifugal force of the spin. Within this zone, something truly incredible happens. Space-time itself is dragged around by the black hole's immense rotation. It's not just matter and light that are pulled along. The very grid of space and time is set into motion, like a powerful whirlpool in the ocean of the cosmos. This effect, known as frame dragging, is so powerful inside the ergosphere that it becomes impossible for any object to remain stationary. Everything, every particle, every photon, the very fabric of reality is forced to rotate with the black hole. You could fight against this current with the most powerful rockets imaginable, and you would still lose. You are compelled to move with the flow of twisted space-time. This bizarre environment isn't just a curiosity, it's a cosmic engine room. The twisted physics of the ergosphere allows for a phenomenon that seems to defy common sense: the extraction of energy directly from a black hole's rotation. This is made possible through a brilliant mechanism conceived by physicist Roger Penrose, aptly named the Penrose process. Here's how it works. Imagine a daring spacecraft ventures into the ergosphere and releases a payload, splitting an object into two parts. Due to the extreme frame dragging and the precise angles involved, one fragment could be flung out of the ergosphere with more energy than the original object entered with, while the other fragment, carrying what is called negative energy, falls past the event horizon into the black hole. This isn't magic, it's rigorous physics. The fragment with negative energy effectively reduces the black hole's mass and rotational energy. The energy for the escaping fragment's boost doesn't come from nowhere. It is quite literally stolen from the spin of the black hole itself. It's the ultimate cosmic heist, and the ergosphere is the vault. This energy extraction process is not merely a theoretical parlor trick. It provides a compelling explanation for some of the most energetic and violent events we observe in the universe. Supermassive black holes at the centers of galaxies often have colossal jets of matter and radiation shooting out from their poles at nearly the speed of light, stretching for thousands of light years. These jets are unimaginably powerful, and their energy source has long been a mystery. The ergosphere and processes like it are prime suspects. As matter swirls into the accretion disk around a black hole, some of it is inevitably channeled into the ergosphere, where these wild energy transactions can take place. The energy extracted from the black hole's spin could be the engine that accelerates particles to such fantastic speeds and powers these brilliant galactic-scale beacons. The ergosphere, therefore, transforms our view of black holes from simple consumers to potential power plants, capable of influencing and energizing entire galaxies. It blurs the line between the black hole's interior and the external universe, proving that the influence of these cosmic giants extends far beyond their event horizons, shaping the cosmos through the incredible dynamics of their spin. But if the inner horizon is a chaotic maelstrom of focused energy, then the Cauchy horizon is something even more profound and unsettling, a true boundary of knowledge itself. Deep within the mathematically complex interiors of charged or rotating black holes, past the inner horizon, lies this final frontier of predictability. Named after the French mathematician Augustin-Louis Cauchy, this horizon isn't a physical barrier you could touch. It's a mathematical point of no return for our ability to forecast events. Up to this boundary, Einstein's equations of general relativity work perfectly. We can chart the path of particles, map the curvature of space-time, and predict the future state of the system with confidence. But the moment we cross the theoretical Cauchy horizon, the equations break down completely. The future becomes fundamentally unknowable using the classical rules of physics. It's not that our calculations get messy, it's that the answers become entirely ambiguous. The laws of physics, as we know them, simply cease to provide a unique outcome, presenting us with an infinite number of possible futures. This represents a mathematical singularity in predictability, a place where the universe itself seems to shrug its shoulders and refuse to tell us what happens next. This breakdown is tied to one of the most extreme phenomena imaginable, the infinite blue shifting of light. As light or any radiation falls inward through the black hole, it gains energy, and its wavelength gets shorter. It becomes blue shifted. Normally, this is a finite process, but the unique geometry near the Cauchy horizon causes this blue shifting to amplify without limit. The energy of incoming radiation is mathematically predicted to skyrocket to infinity over a finite time. Picture the entire history of the universe, all the starlight, cosmic background radiation, and energy that has ever fallen into the black hole, focused and amplified into an infinitely energetic, infinitely concentrated wall of radiation right at this boundary. This phenomenon, often called the problem of mass inflation, suggests the Cauchy horizon is likely not a stable, peaceful gateway, but a seething region of unimaginably destructive energy that would obliterate anything approaching it. In this view, the Cauchy horizon acts as a final, violent physical barrier, a natural firewall that protects the sanctity of causality from the paradoxes that might lie beyond. However, the sheer weirdness of this mathematical boundary has led to other, far more speculative interpretations. If predictability breaks down, could the rules of cause and effect break down with it? Some physicists have explored the tantalizing possibility that the region beyond the Cauchy horizon could contain closed time-like curves, paths through space-time that loop back on themselves, effectively allowing for time travel. In this scenario, crossing this horizon might not lead to destruction but to a realm where you could, in theory, travel into your own past. Other speculations suggest it could be an exit, a gateway that doesn't lead to a singularity but to another universe entirely, a separate branch of reality with its own physical laws. These ideas remain firmly in the realm of theoretical exploration, as the instability of the horizon makes such journeys seem impossible. Yet, the very fact that our most successful theory of gravity allows for such possibilities, even if they are likely physically forbidden, is a breathtaking reminder of how strange the universe can be at its absolute limits. Ultimately, the Cauchy horizon serves as a stark and humbling reminder. It is the clearest signpost that deep inside a black hole, in its most hidden depths, our trusted classical tools of general relativity are no longer sufficient. The equations that have so perfectly described the cosmos from the orbit of Mercury to the bending of light around galaxies finally meet their match. They do not just become difficult to compute. They fundamentally fail, yielding nonsense answers like infinite energy. This tells us more clearly than almost anything else that to truly understand the core of a black hole, we cannot rely on Einstein's theory alone. We must have a theory that marries gravity with the quantum world, a theory of quantum gravity that can step in where classical physics falters, and perhaps finally tell us what truly lies on the other side of this ultimate veil of unpredictability. But if the Cauchy horizon represents a boundary where our classical understanding of physics dissolves into ambiguity, the next hidden structure takes us directly into the heart of that ambiguity, proposing a radical reinvention of the black hole's core. We are moving beyond the notion of a simple, infinitely dense point, and into a realm where the very fabric of spacetime becomes a churning, probabilistic sea. This brings us to our eighth hidden structure, a concept that reimagines the terrifying singularity as something far stranger and more dynamic: quantum foam. The classical singularity has always been the most troubling aspect of black hole theory. It's a place where the known laws of physics break down, where density and curvature become infinite, and our equations return nothing but error messages. For decades, physicists have understood that this isn't a feature of nature but a flaw in our theory, a glaring sign that Einstein's general relativity, while magnificent, is incomplete. It doesn't incorporate the rules of the quantum world that govern the very small. To resolve this, theories of quantum gravity step in, and one of their most compelling proposals is that the cold, dead singularity is an illusion. In its place, they suggest the center of a black hole is a seething, effervescent froth known as quantum foam. Envision spacetime not as a smooth, continuous sheet, but as something more like the head on a glass of soda. At the unimaginably tiny Planck scale, a distance of 10 to the minus 35 meters, the fabric of reality is not calm and still. It is a chaotic, probabilistic foam. Tiny bubbles of spacetime constantly pop into and out of existence. Microscopic wormholes flicker open for a fleeting instant, connecting disparate points before vanishing again. Virtual particles dance in a frenetic foam, and the very concepts of here and there, before and after, lose their absolute meaning. In this foam, geometry itself is fuzzy and uncertain. You cannot say precisely where a point is located or how spacetime is curved at that exact scale. You can only speak in terms of probabilities. This isn't a flaw. It's the fundamental nature of reality according to quantum principles, and it becomes the dominant feature at the heart of a black hole, where matter is compressed to its ultimate limit. This idea emerges from two of the leading contenders for a theory of quantum gravity: loop quantum gravity and string theory. Both approaches, in their own ways, suggest that spacetime has a discrete, granular structure when you zoom in far enough. Loop quantum gravity proposes that space is woven from tiny, finite loops, and their interactions prevent the infinite compression of a singularity. Instead, you get a rebound or a transition into this foamy state. String theory, with its vibrating strings and higher dimensions, also points toward a similar conclusion: that what we perceive as a singularity is actually a dense, stringy, foamy medium where the old rules of geometry no longer apply. The implications of a quantum foam core are profound. It transforms the black hole from a cosmic trash compactor, where everything is crushed into nothingness, into a vibrant quantum landscape. It is not a static endpoint, but a dynamic, bubbling region of immense energy and constant change. This foamy heart could potentially store information in the complex fluctuations of spacetime itself, offering a natural solution to the information paradox. It suggests that the center of a black hole is not a place of death and erasure, but a zone of extreme quantum activity, where the building blocks of reality are constantly rearranged in a chaotic, yet law-governed dance. This vision replaces the chilling finality of the singularity with a picture of a universe that remains creative and active, even under the most extreme conditions, forever hiding a storm of quantum potential at the center of its darkest objects. Yet if the quantum foam hints at a turbulent, chaotic heart, our next hidden structure proposes a far more elegant and breathtaking possibility, one that transforms the entire nature of a black hole's destiny. What if the inward collapse of matter doesn't end in a frothing quantum sea or a fiery wall, but instead reverses into a magnificent cosmic rebirth? This idea ventures beyond mere endpoints and into the realm of cosmic symmetry, suggesting that for every black hole that swallows, there could be a white hole that gushes forth. We are now exploring the astonishing theory of the white hole fountain. The concept is rooted in the beautiful symmetry of Einstein's equations of general relativity. Just as these equations predict the existence of black holes, regions where matter and energy can fall in but never escape, they also mathematically permit the existence of their exact opposite, white holes. A white hole would be a region of spacetime where matter and energy can explosively erupt outward, but nothing can ever enter. It is a cosmic fountain of creation, a one-way exit door from a hidden source. For decades, white holes were considered little more than a mathematical curiosity, a quirky but physically impossible flip side of the black hole solution. But what if they are not separate objects at all? What if they are intrinsically linked? This is where the theory gets truly revolutionary. Some cosmological models propose that a black hole and a white hole are two connected parts of a single structure. The black hole is the entrance and the white hole is the exit. The interior of the black hole, then, wouldn't house a singularity but would instead contain a tunnel, a bridge, that connects the two. This is the essence of an Einstein-Rosen bridge, more popularly known as a wormhole. Imagine a dying star collapsing into a black hole. According to this model, the incredible gravitational forces wouldn't crush it into oblivion. Instead, the extreme warping of spacetime could forge a tunnel, a throat, that connects to a white hole in a distant part of our universe, or even in a completely different universe altogether. The infalling material would plunge through this tunnel, avoiding the paradox of infinite density, and would then be violently ejected out of the white hole fountain on the other side. In this view, a black hole is not a grave. It is a cosmic expressway, a transfer point in the grand network of the multiverse. The matter it consumes isn't destroyed, it is simply relocated, shot across the cosmos in a brilliant eruption of new energy. This idea of a connected tunnel is mathematically elegant, but it faces a colossal problem: stability. The classic Einstein-Rosen bridge described in the 1930s was calculated to be incredibly fragile. The moment any matter or energy tried to pass through it, the tunnel would collapse instantaneously, snapping shut and crushing whatever was inside, effectively becoming a traditional singularity. This seemed to relegate the wormhole concept to the realm of science fiction. However, modern theoretical physics has not given up on the dream. Some proposals suggest that exotic forms of matter with negative energy density, something we have glimpsed in tiny amounts in quantum effects like the Casimir effect, could theoretically be used to prop the tunnel open, reinforcing it against collapse and making it traversable. While we are far from finding or creating such exotic matter in sufficient quantities, its theoretical possibility keeps the idea of a stable white hole fountain alive. The implications of this are, of course, staggering. It suggests that the universe might be far more interconnected than we ever dreamed. Black holes could be the seeds of new universes, with the Big Bang itself being the ultimate white hole eruption. Or they could be portals allowing for travel across vast cosmic distances or even through time, fulfilling the wildest fantasies of science fiction. While it remains one of the most speculative ideas on our list, the white hole fountain represents a profound shift in perspective. It challenges the grim finality of the classical black hole, and offers a vision of the cosmos that is not just destructive but endlessly creative, where death in one corner of reality can mean birth in another. But what if the chaotic quantum foam or the tunnel to a white hole aren't the only possibilities? What if the immense pressure at the center of a black hole doesn't lead to a frothing sea of space-time or a gateway, but instead forces matter into a state of perfect, coherent, and eerie quantum order? To explore this, we must leave the vastness of space and venture into the realm of the ultra-cold, into a state of matter so strange it was only created in laboratories a few decades ago. This brings us to our 10th hidden structure, a concept that sees the heart of a black hole not as a point of destruction, but as a perfectly unified quantum entity, the Bose-Einstein condensate. In everyday life, we're used to matter behaving in predictable ways. Atoms and molecules bounce around, each one an individual following its own path, like a bustling crowd of people. But when you cool certain types of matter to temperatures a mere whisper above absolute zero, something almost magical happens. These individual particles lose their identities. They slow down so much that their quantum mechanical wave functions, the probability clouds that describe their location, begin to overlap and merge. They cease to be a crowd and instead become a single, giant, coherent superatom, all acting in perfect unison. This is a Bose-Einstein condensate, a state of matter first predicted by Satyendra Nath Bose and Albert Einstein in the 1920s, and finally created in a Colorado lab in 1995, a discovery that won the Nobel Prize. In this exotic state, matter behaves less like a collection of particles and more like a single wave. It becomes a superfluid, a substance with zero viscosity that can flow without any friction whatsoever, even climbing up the walls of its container and dripping out. Now, transfer this concept from an ultra-cold lab on Earth to the most extreme environment in the universe, the core of a black hole. The conditions there are the polar opposite of a lab freezer. It is a place of unimaginable heat and pressure from the crushing weight of infalling matter. Yet, some quantum theories propose that this very pressure could achieve a similar result. The idea is that the incredible density forces all the particles, the protons, neutrons, electrons, and whatever exotic forms they take under such duress, to be squeezed so close together that their quantum wave functions can't help but overlap. They would be compelled to surrender their individuality and merge into a single, macroscopic quantum object, a Bose-Einstein condensate core. This wouldn't be a cold condensate like in our labs, but a super-dense, super-hot one held in a delicate balance. The quantum pressure generated by this coherent state, a repulsive force arising from the inherent uncertainty of the particles' positions, could act as a perfect counterweight to the immense gravitational pull, preventing a total collapse into a singularity. The core would be stabilized, not by nuclear forces or exotic matter, but by the fundamental rules of quantum mechanics themselves. This vision of the black hole's interior is profoundly elegant. It suggests that deep within this ultimate symbol of chaos and destruction, there could be a realm of perfect, silent order. Instead of a frenetic quantum foam, you would have a superfluid quantum ocean, a single coherent entity swirling with a strange, wave-like grace. It would have zero viscosity, meaning there would be no internal friction. Any motion or disturbance within this core would propagate perfectly and endlessly. This could explain how a black hole can maintain a stable structure without a problematic singularity. The condensate core is the structure. It also forges a stunning and unexpected bridge between two seemingly disconnected fields of physics: the study of ultra-cold atoms in a lab and the study of ultra-dense objects in deep space. It implies that the same quantum principles that govern the behavior of a few million atoms cooled to near absolute zero in a magnetic trap might also govern the behavior of the mass of entire stars compressed into a tiny space. The heart of darkness in this view is not a void but a hidden quantum ocean, a perfectly unified entity humming with a silent, coherent energy, representing a state of matter so exotic it redefines our understanding of stability under pressure. Yet if the Bose-Einstein condensate imagines a core of perfect quantum order, our next hidden structure proposes a reality so radical it challenges the very notion of an inside at all. This idea doesn't just reshape the black hole's interior. It suggests that the interior, as we conceive of it, might not even physically exist. We are now stepping into one of the most profound and mind-bending concepts in all of theoretical physics, the holographic principle, and its vision of the black hole as a cosmic hologram. The story begins not with black holes, but with a deep puzzle about information. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's entropy, a measure of its hidden information or disorder, was not proportional to its volume as it is for every other object in the universe. Instead, it was proportional to the surface area of its event horizon. This was bizarre. Imagine a hard drive. Its storage capacity depends on its three-dimensional volume. But a black hole, the ultimate cosmic hard drive, seemed to store all its information on its two-dimensional surface. Stephen Hawking later confirmed this with his work on Hawking radiation, cementing the idea that the amount of information a black hole could contain was defined by the area of its boundary, not the space within it. This odd fact was a tantalizing clue that physicists would ponder for decades. The true revolution came from string theory, specifically from a groundbreaking discovery known as the anti-de Sitter/conformal field theory correspondence, or ADS/CFT. In the late 1990s, physicist Juan Maldacena proposed a stunning duality. He showed that a gravitational theory describing a warped volume of space, a kind of abstract universe with a specific type of curvature, was completely equivalent to a quantum field theory operating on that volume's lower dimensional boundary. In simpler terms, a universe with gravity in three spatial dimensions could be perfectly described by a set of physical laws that only exist on its two-dimensional surface. There is no gravity in the surface theory, and no particles in the bulk theory. They are two utterly different but mathematically identical descriptions of the same reality. It was as if the entire, rich, three-dimensional world we experience was nothing more than a projection, a hologram encoded on a distant, two-dimensional screen. Now apply this breathtaking principle to a black hole. The ADS/CFT correspondence suggests that the black hole's entire three-dimensional interior, all the swirling matter, the warped spacetime, the terrifying descent toward the center, is not the fundamental reality. It is an emergent illusion. The true reality, the complete description of the black hole and everything that has ever fallen into it, is encoded on its two-dimensional event horizon. Every particle, every atom, every bit of information about an object that crosses the boundary is not lost inside. It is smeared and stored across the horizon's surface, imprinted there in unimaginably tiny Planck scale units of area. The horizon becomes the ultimate information storage device, a cosmic hard drive with a maximum data density set by the laws of quantum gravity. This forces us to completely redefine what it means to fall into a black hole. From the perspective of someone outside, an object never actually crosses the horizon and enters a void. Instead, its information is encoded onto the surface, and from that moment on, the interior we talk about is just a complex, holographic projection of that surface data. It's like a character in a video game. The character exists and moves in a rich, three-dimensional world on your screen, but its entire existence is actually just a representation of data encoded on the two-dimensional surface of the computer's processor. The interior of the black hole is the projection, the horizon is the processor. This resolves the information paradox with elegant finality. Information is never lost because it never enters a singularity to be destroyed. it remains forever stored on the horizon and can eventually be radiated back out via the intricate process of Hawking radiation. The implications of this are nothing short of metaphysical. It suggests that our intuitive understanding of reality, that we live in a three-dimensional world, might be a deep illusion. The holographic principle hints that the entire universe could, at its most fundamental level, be a vast hologram, with its physical laws and contents encoded on a distant, lower dimensional boundary. For the black hole, this means there is no there. The heart of darkness is not a place of mysterious structures, but a magnificent illusion, a dynamic and incredibly complex projection of data. The black hole is transformed from a gravitational monster into an informational phenomenon, a testament to the idea that at the most fundamental level, the universe may not be made of stuff, but of information. Yet even as the holographic principle redefines the very nature of interior space, another hidden structure proposes that black holes might contain something far more tangible and mysterious than information, something that makes up the vast majority of matter in the universe yet remains completely invisible to us. This brings us to our 13th hidden structure, a concept that links the enigma of black holes to the greatest unsolved puzzle in cosmology, the dark matter core. For decades, astronomers have known that the universe holds a secret. Galaxies rotate too fast for the amount of visible matter they contain, and galaxy clusters are bound together by a gravity that far exceeds what their stars and gas can provide. The only explanation is that there is something else there, a form of matter that does not emit, absorb, or reflect light, hence the name dark matter. It makes up about 85% of all matter in the cosmos, and yet we have no idea what it is made of. We can only detect it through its gravitational influence. Now, consider the most powerful gravitational wells we know of, black holes. It stands to reason that these cosmic vacuum cleaners would not only suck in stars and gas, but also vast amounts of this invisible dark matter. But what happens to it once it's inside? Does it simply plunge into the singularity like everything else? Or could it accumulate into something entirely different? Some compelling theories suggest that dark matter, because it does not interact with light or with itself in the same way normal matter does, might not collapse into an infinitely dense point. Instead of being compressed into a singularity, the dark matter particles could form a stable, diffuse ball at the very center of the black hole, a massive, invisible core. This dark matter core would be held in a delicate balance, its own gravitational pull countered by the innate kinetic energy or quantum pressure of the dark matter particles themselves. It wouldn't be a point, but an extended structure, a huge sphere of pure, undetectable mass lurking within the heart of the black hole. This core could potentially influence the black hole's behavior in subtle ways, perhaps affecting its rate of spin, its growth over time, or even the way it merges with other black holes. It might explain certain anomalies in the gravitational wave signals we've detected from black hole collisions, hints that their internal structure might be more complex than a simple singularity. This idea powerfully connects two of the most profound mysteries in modern physics. The search to understand black holes and the search to understand dark matter might not be separate quests. They could be intimately linked. The darkest objects in the universe might be hiding the darkest substance in the universe at their very centers. A supermassive black hole at the center of a galaxy, in this model, wouldn't just be sitting there. It would be continuously feeding on and harboring a massive ball of the very stuff that shapes the galaxy's destiny. The dark matter core transforms the black hole from a simple consumer of light into a guardian of shadow, a hidden heart of invisible mass that could hold the key to unraveling the true nature of most of the matter in the cosmos. Yet if the holographic principle suggests the black hole's interior is an informational illusion, our next hidden structure grounds us back in a tangible, if invisible, cosmic substance. This idea proposes that black holes may act as cosmic traps, capturing and concentrating the universe's most elusive material right at their hearts. We're venturing into the possibility that within these gravitational giants lies a secret core not of blazing energy or warped spacetime, but of something far more mysterious: dark matter. For decades, astronomers have been confronted with a cosmic puzzle. When they measure the rotation of galaxies, they find that the stars at the outer edges are moving far too quickly to be held in place by the gravitational pull of all the visible matter, the stars, gas, and dust we can see. The same is true for entire clusters of galaxies. Their visible mass is insufficient to generate the gravity that binds them together. The inescapable conclusion is that there must be something else there, a form of matter that exerts a gravitational pull but does not interact with electromagnetic forces. It doesn't emit, absorb, or reflect light, rendering it completely invisible to our telescopes. This mysterious substance is dark matter, and it makes up roughly 85% of all the matter in the universe. We know it's there by the gravitational shadow it casts, but its fundamental nature remains one of the biggest unsolved problems in all of physics. Now, consider the ultimate gravitational sinkhole, a black hole. Its immense pull draws in everything nearby: stars, gas clouds, and presumably any dark matter that happens to be in the vicinity. But here's where the theory gets fascinating. Normal matter, like gas and dust, interacts with itself. As it spirals inward in an accretion disk, friction and collisions cause it to heat up, radiate energy, and lose angular momentum, allowing it to eventually cross the event horizon. Dark matter, by its very definition, is different. It doesn't interact electromagnetically, and it's theorized to have very weak interactions with itself, if any at all. This means dark matter particles could fall directly toward the black hole without forming a hot, radiating disk. They would simply plunge inward on nearly straight trajectories, accumulating in the deepest part of the gravitational well. But what happens to this dark matter once it's there? Unlike normal matter, which is thought to collapse into a singularity under the extreme pressure, dark matter might behave entirely differently. Because it doesn't experience the same pressure-inducing collisions, it might not collapse to a point. Instead, the dark matter particles could end up orbiting within a vast region at the center, forming a massive, diffuse, and stable core. A huge, invisible ball of pure dark matter right at the heart of the black hole. This core wouldn't be a singular point but an extended structure, a sphere of incredible mass that remains perfectly transparent and undetectable by any means other than its gravity. It would be a ghostly heart within a dark beast. The presence of such a core could have observable consequences, subtly influencing the black hole's behavior and development. A supermassive black hole with a large dark matter core might grow at a different rate, spin differently, or even merge with other black holes in a distinctive way that could leave a faint imprint in the gravitational wave signals we detect. This idea forges a powerful link between two of the greatest mysteries in modern cosmology: the nature of black holes and the nature of dark matter. It suggests that the darkest objects in the universe might be the natural repositories for the universe's darkest substance. The supermassive black hole at the center of a galaxy wouldn't just be sitting there. It would be continuously fed by and cradling a massive ball of the very material that dictates the galaxy's structure and fate. This transforms our view of black holes from simple consumers of light into guardians of shadow. They're hidden, invisible cores potentially holding the key to understanding the true fabric of the cosmos. But if the dark matter core suggests a hidden, massive heart, our next structure ventures into the realm of the incredibly small, proposing that the fabric of spacetime itself is riddled with shortcuts. Imagine the crushing density at the center of a black hole not as a solid wall, but as a labyrinth, a complex, ever-changing web of tunnels that could offer a way out of the ultimate cosmic trap. This brings us to a concept where the bizarre rules of the quantum world rewrite the map of reality inside a black hole, the quantum tunnel network. This idea springs from the work of legendary physicist John Wheeler, who envisioned that at the tiniest possible scales, the vacuum of space is not empty and smooth. Instead, it is a chaotic, frothing sea now known as quantum foam. In this foam, the very concepts of distance and location become fuzzy. Tiny fluctuations in energy constantly create pairs of virtual particles that pop in and out of existence. But Wheeler took this further, suggesting that these fluctuations could also warp the fabric of spacetime itself, creating a vast network of minuscule, transient wormholes, tiny bridges connecting one point in space to another. These aren't the stable, traversable wormholes of science fiction. They are Planck-scale tunnels that form and dissolve in an instant, a fundamental part of the foamy texture of reality. Now, place this quantum foam under the immense pressure of a black hole's interior. The extreme conditions could amplify this natural tendency of spacetime to tunnel. Instead of just microscopic, fleeting connections, the quantum gravitational forces might stabilize and expand this network, weaving these tiny tunnels into a vast, complex labyrinth within the black hole. This would not be a single, large wormhole, but an intricate web of quantum shortcuts, connecting different regions inside the black hole to each other in a non-linear way. And particle falling inward wouldn't necessarily have to travel a straight line to the center. It could suddenly find itself taking a quantum shortcut, popping from one point to another without passing through the space in between. This network could provide a mechanism for information to be distributed and processed throughout the black hole's interior, avoiding a direct plunge into a destructive singularity. The information isn't lost, it's just taking a complex route through a hidden cosmic maze. The implications of such a network are profound, especially for the black hole information paradox. If information entering a black hole is immediately scattered and transmitted through this vast internal web of tunnels, it could be preserved and potentially even retrieved. This labyrinth would act as the ultimate quantum computational network, a natural system for scrambling and processing information at the most fundamental level. Furthermore, some of these quantum tunnels might not just connect points within the same black hole. The mathematics suggests that they could also form connections to other regions of spacetime entirely, perhaps to other black holes, or even to other universes in a vast multiverse. While traversing these tunnels would be incredibly unlikely for any macroscopic object, the possibility exists in theory, painting a picture of black holes not as endpoints, but as potential nexus points in a much larger cosmic network. This vision transforms the black hole interior from a simple, doomed void into a dynamic and incredibly complex quantum structure. It is no longer a place of certain death, but a realm of quantum potentiality, where the usual rules of geometry are replaced by a probabilistic web of connections. The quantum tunnel network suggests that at its heart, a black hole is less like a pit and more like a bustling quantum teleportation hub, where information and energy are constantly routed through a hidden labyrinth, forever preserving the data of what fell in and perhaps even offering secret passageways to realities beyond our own. But if the quantum tunnel network imagines a labyrinth of hidden passageways, our next structure proposes a different kind of internal architecture, one not of physical tunnels, but of organized layers of increasing chaos. We've seen that black holes have entropy, a measure of their hidden information. But what if this disorder isn't uniform? What if the heart of darkness has its own structured gradient of chaos, a cosmic onion with layers of ever-deepening complexity? This brings us to the 15th hidden structure, a concept that transforms the black hole from a simple pit into a dynamically organized system, the entropy gradient. The story of black hole entropy is itself a fascinating twist in physics. In the 1970s, Jacob Bekenstein made the revolutionary proposal that black holes must have entropy. This was shocking because entropy, a concept from thermodynamics, is usually associated with disorder in a system of many parts, like the molecules in a gas. A black hole, according to classical general relativity, was supposed to be the simplest object in the universe, defined only by its mass, charge, and spin, a concept enshrined as the no-hair theorem. It had no parts, no internal structure, and thus, seemingly, no disorder. But Bekenstein, inspired by a thought experiment, realized that if you threw something with high entropy into a black hole, the entropy of the universe would appear to decrease, violating the second law of thermodynamics. His brilliant solution was that the black hole itself must gain entropy to compensate, and he found that this entropy was proportional to the surface area of its event horizon, not its volume. Stephen Hawking later cemented this idea by showing black holes have a temperature and emit radiation, forging an indelible link between gravity, quantum mechanics, and thermodynamics. Now, let's venture inside. If the total entropy is a property of the surface, what does that imply for the interior? Some theories suggest this surface entropy is just the total sum, and that inside, the distribution of this information isn't even. They propose an entropy gradient, a structured change in disorder from the event horizon down toward the center. Picture it like diving into the ocean. Near the surface, the water might be warmer and more turbulent, but as you descend, the pressure increases, the temperature drops, and the environment becomes more extreme and alien. In a similar way, the entropy gradient suggests that the region just inside the event horizon might be a zone of lower entropy, where information is still being processed and integrated. As you plunge deeper, the entropy, the disorder and the complexity of the information stored, would steadily increase, reaching its maximum at the very core. This isn't a gradient of physical matter, but a gradient of information density and complexity. This internal organization would have dramatic physical consequences. In thermodynamics, entropy is intimately connected to temperature. A gradient in entropy could manifest as a gradient in temperature or energy density, creating distinct layers or zones within the black hole. The outermost layers might be colder in an informational sense, while the inner layers would be seething hotbeds of quantum complexity. This structured interior could influence how infalling matter is assimilated. Instead of everything being immediately crushed to a point, matter might be digested in stages, its information processed and its energy distributed according to this deep internal structure. It portrays the black hole not as a simple trash compactor, but as a sophisticated cosmic engine with an internal thermodynamic geography. Much like a star has distinct layers like a core, a radiative zone, and a convection zone. The existence of an entropy gradient would be a powerful sign that black holes are far from the simple, featureless objects of classical theory. It reveals them as dynamic systems with a rich internal life, governed by the laws of quantum statistics and information theory. They are not merely traps, they are processors. They have an anatomy of disorder, a hidden architecture that dictates how they store the universe's secrets. This gradient is the ultimate expression of the holographic principle in action, the idea that the information on the surface dictates the reality within. The increasing entropy toward the center would reflect the ever-deepening complexity of that holographic projection, suggesting that the true heart of a black hole is not a place of simplicity, but the most complex and disordered library in the cosmos. Yet, as we consider the intricate organization of an entropy gradient, we must also account for the raw, dynamic power of a black hole's spin, a force so potent it could sculpt the very fabric of spacetime into a hidden, crystalline architecture. Picture the immense vortex of a rotating black hole, a cosmic maelstrom where spacetime is not merely warped but whipped into a frenzy. Within this whirling darkness, Some theories suggest that the rotation doesn't just create chaos, it generates a stunning and ordered pattern, a geometric dance of swirling energy known as a vortex lattice. This concept emerges from a powerful analogy between the most massive objects in the universe and some of the most delicate phenomena observed in laboratories on Earth. In the field of condensed matter physics, when certain superfluids or Bose-Einstein condensates are set into rapid rotation, they don't simply form a featureless whirlpool. Instead, they spontaneously develop a perfectly regular array of microscopic whirlpools, a grid-like pattern of vortices that resembles a honeycomb or lattice. Each vortex is a tiny tornado of swirling fluid, and they arrange themselves into a precise, repeating pattern to most efficiently distribute the angular momentum. This is a well-documented and beautiful phenomenon, a signature of quantum order emerging from chaos. Now, transfer this principle to the ultra-dense, hyper-rotating environment inside a Kerr black hole. The interior is often described as a kind of fluid, a dynamic, swirling medium of spacetime and energy. The mathematics suggests that under such extreme rotational stress, this spacetime fluid might undergo a similar phase transition, organizing itself not into a random mess, but into a vast, intricate lattice of massive vortices. Each vortex in this hidden lattice would be a colossal tornado of twisted spacetime and energy, potentially stretching from the inner horizon toward the center. These wouldn't be gentle swirls, they would be structures of immense power, acting as cosmic conduits that channel and focus the black hole's furious spin. Matter and energy falling into the interior wouldn't just plunge straight down. They would be caught in these gravitational currents, forced to spiral along the lattice lines in a complex, orchestrated flow. This could create powerful internal circulation patterns, perhaps even feeding jets of energy that align with the black hole's axis of rotation. The stability of this lattice would be key. It might be a fixed, permanent structure that helps regulate the black hole's spin over eons, or it could be oscillatory, pulsating and shifting in a way that causes the black hole to wobble or ring like a bell, emitting a specific signature in its gravitational waves. The existence of a vortex lattice would profoundly change our understanding of a black hole's interior geometry. It would mean that deep within the apparent chaos, there is a hidden order, a crystalline structure forged from pure gravity and angular momentum. This isn't the featureless void of classical theory. It's a dynamic, organized arena with its own complex topography. The vortex lattice acts as a hidden engine, translating the raw power of spin into a structured flow that dictates how the black hole processes energy, stabilizes itself, and interacts with the universe outside its event horizon. It reveals a black hole not as a simple trap, but as a sophisticated cosmic organism with a circulatory system woven from the twisted threads of spacetime itself. But if the vortex lattice represents an architecture of ordered motion, our next hidden structure plunges us into the heart of pure chaos, a chaos that is not destructive, but rather profoundly creative. We now arrive at a concept that sees the black hole not as a gravitational prison, but as the universe's most powerful and efficient information processor. At the core of this idea is a mechanism so fast and so thorough that it can take the most complex data and render it into a fundamental, featureless form, only to have it perfectly preserved. This is the information scrambler, and it is the key to solving one of the most enduring puzzles in physics. The puzzle is the black hole information paradox, and it begins with a simple question: what happens to the information about an object that falls into a black hole? Quantum mechanics, the rulebook for the universe, states with absolute certainty that information can never be truly destroyed. It can be changed, transformed, or hidden, but it must always, in principle, be recoverable. Yet, the classical view of a black hole presents a terrifying problem. When something crosses the event horizon, it appears to be lost forever, eventually crushed into the singularity, its unique identity seemingly erased from existence. Stephen Hawking's own work initially suggested that when a black hole evaporates through the radiation that bears his name, it only emits random thermal noise, carrying no information about what was inside. This would mean the information is permanently lost, a direct violation of quantum law. This paradox set off a crisis in theoretical physics that has lasted for decades. The Scrambler is the brilliant resolution to this crisis. It proposes that the black hole's interior contains a specific region or mechanism, a kind of quantum chaotic blender, that takes the information of anything that falls in and rapidly mixes it. This isn't a slow process. It happens at speeds approaching the Planck scale, the fastest possible rate allowed by the laws of physics. Imagine throwing a beautifully detailed, multi-colored sand painting into a giant cosmic mixer. The Scrambler doesn't destroy the sand. It violently tosses every single grain, blurring the beautiful picture into what looks like a uniform, beige mush. To an outside observer, the information, the original painting, seems to be gone, but in reality, every grain of sand is still there. Their positions have just been randomized and their colors perfectly mixed. The information is not lost. It has been scrambled and distributed evenly throughout the entire system. Inside a black hole, this system is the event horizon itself, in line with the holographic principle. The Scrambler takes the quantum information of an infalling star, spaceship, or particle, and rapidly encodes it onto the microscopic Planck scale pixels that make up the black hole's surface area. It does this through a property unique to quantum systems called entanglement, weaving the new information into an incredibly complex web of connections with all the information that has ever fallen in. The process is so efficient and so fast that the information becomes holographically smeared across the entire horizon, becoming a fundamental part of the black hole's identity. Then, when the black hole emits Hawking radiation, it isn't just random thermal noise. Each particle of radiation is subtly entangled with this scrambled information on the horizon. As the radiation leaks out, it slowly and faithfully carries the scrambled information back into the universe, like individual grains of sand being blown out of the mixer, one by one. By the time the black hole fully evaporates, all the information has been returned, preserving the sacred law of quantum mechanics. This transforms our view of a black hole from a cosmic shredder into the ultimate quantum computer. Its interior is not a silent void but a buzzing, chaotic data center, performing calculations at the literal maximum speed allowed by nature. The Scrambler is the engine of this computation, a natural mechanism that ensures the universe never forgets. It takes the unique stories of everything it consumes and weaves them into the most complex tapestry imaginable. A tapestry painted on the surface of the abyss, proving that even in the heart of darkness, there is no such thing as true erasure, only transformation. Yet even as the information scrambler ensures that data is never truly lost, another hidden structure proposes that the universe itself might enforce a different kind of preservation, not of information, but of predictability. This idea confronts one of the most unsettling possibilities allowed by Einstein's equations, the naked singularity. It suggests that deep within the black hole's interior, a hidden mechanism acts as a cosmic editor, censoring the most chaotic aspects of reality to protect the logical consistency of the universe beyond the event horizon. This is the principle of cosmic censorship, and it may be more than just a conjecture. It could be an active, physical structure. The problem begins with the mathematics of general relativity. Einstein's glorious equations, which so accurately describe the warping of spacetime, sometimes spit out solutions that are deeply disturbing. They allow for the possibility of a naked singularity, a point of infinite density that is not hidden behind an event horizon. This would be a region where the laws of physics completely break down, but its catastrophic gravitational and causal influences would be exposed for the entire universe to see. Imagine a point where gravity becomes infinite, where time could loop back on itself, and where the very concept of cause and effect ceases to have any meaning. Now imagine that point just sitting out in the open, visible and able to influence the cosmos around it. The consequences would be catastrophic for physics, as it would become impossible to predict the future of anything that interacted with this monstrous anomaly. The universe would be fundamentally unpredictable. To rescue physics from this nightmare, the renowned physicist Roger Penrose proposed the cosmic censorship conjecture. In its simplest form, it states that nature abhors a naked singularity. The conjecture argues that any singularity that forms through the realistic gravitational collapse of a star will always be hidden from view, carefully wrapped and concealed behind an event horizon. This horizon acts as a protective barrier, a kind of one-way curtain that contains the infinite insanity within, ensuring that the outside universe remains a place where the laws of physics are dependable and predictions can be made. For decades, this has been a foundational, though unproven, assumption in general relativity, a hopeful statement that the universe maintains a sense of decorum. But what if this censorship isn't just a passive law of nature, but is actively enforced by a physical structure inside the black hole? Some theories in quantum gravity suggest exactly that. They propose that the interior houses a cosmic sensor, a region or mechanism powered by quantum, gravitational effects that actively works to prevent a singularity from becoming naked. This sensor might not be a literal sentinel, but a dynamic process. For instance, as matter collapses toward what would become a singularity, the incredible rise in energy and density could trigger a phase transition in spacetime itself. Quantum effects might smooth out the infinite sharpness of the singularity, replacing it with a fuzzy, Planck-length-sized region of extreme but finite density, like the quantum foam or Planck star we discussed earlier. Alternatively, the sensor could manifest as an energetic barrier or a domain of intense chaos that effectively cloaks the singularity, making it impossible to observationally pinpoint or define, even from within the black hole. This hidden guardian ensures that the terrifying reality of a breakdown in physics remains a private affair, locked away from the rest of the cosmos. It upholds the principle that the universe, for all its extreme phenomena, is ultimately orderly and comprehensible. The cosmic sensor is the ultimate embodiment of the idea that nature protects itself from its own most extreme potentialities, maintaining a universe where science is possible, and the future is not a random gamble dictated by visible points of infinite chaos. It is a silent, unseen enforcer of cosmic law, working in the deepest darkness to preserve the light of predictability for everyone else. But what if the cosmic sensor's job is not merely to hide a singularity, but to guard something far more profound? A secret nursery where entirely new universes are born. This leads us to a theory so expansive it redefines a black hole's purpose in the cosmos, suggesting these objects are not endpoints but genesis points. We now explore a hidden structure that connects the fate of a single black hole to the ultimate fate of all reality, the false vacuum bubble. To understand this staggering idea, we must first grasp a peculiar property of our universe's very foundation. In quantum field theory, the vacuum of space is not truly empty. It is filled with a background energy field that dictates the laws of physics as we know them, the strengths of forces, the masses of particles, the speed of light. For a long time, we assumed this vacuum state was stable and unique, the one true and lowest energy state possible. But many physicists now suspect our universe exists in a false vacuum. Imagine this like a ball resting in a small valley on the side of a much larger mountain. The valley is stable for now. The ball isn't moving, but it's not the absolute lowest point it could be. There is a deeper, more stable valley far below, the true vacuum. Our universe's laws are defined by the shape of our current valley. But if something were to knock that ball out of our valley, it would tumble down to that lower, truer state, and in the process, the fundamental constants of physics would change in a cataclysmic event known as a vacuum decay. This is where black holes enter the picture in the most dramatic way possible. The interior of a black hole is a place of unimaginable energy and density, a crucible where the very rules of quantum field theory are pushed to their absolute limits. Some theories propose that these extreme conditions could provide the necessary kick to knock a tiny region of space out of our false vacuum state. Deep inside the black hole, a microscopic bubble of true vacuum could spontaneously form. In this bubble, the laws of physics would be completely different from our own. The strength of gravity, the nature of light, the very number of dimensions could be altered. It would be a pocket of an entirely new reality, governed by its own unique set of physical laws. The fate of this newborn bubble is a cosmic tug of war. The immense gravitational pressure of the black hole surrounding it is trying to crush it out of existence. But the new true vacuum state, by its very nature, possesses a powerful negative pressure, a kind of repulsive gravity that is trying to expand. If the bubble is too small or its new vacuum energy is too weak, the black hole's gravity will win and the bubble will collapse. But if conditions are just right, if the bubble's internal repulsion is strong enough to overcome the crushing weight of the surrounding black hole, it could stabilize. It could even begin to expand. And this expansion would not be stopped by the black hole's event horizon, because the bubble is creating its own new spacetime from within. It would expand through the black hole, not into our universe, but into its own new dimension, instantly disconnecting from our cosmos. In this scenario, the black hole is not a tunnel to another place in our universe, but a gateway to an entirely new universe altogether. The black hole becomes a cosmic womb, and its gravitational collapse is the labor pain of a new reality. This transforms our entire perspective on black holes. They are no longer just consumers of matter and energy, they are potential creators. Each black hole could be a cosmic incubator, a laboratory where the laws of physics are remade. A supermassive black hole at the center of a galaxy might not be a dark monster, but a silent engine of genesis, possibly having already given birth to countless daughter universes with physical laws completely alien to our own. This idea, often called cosmological natural selection, suggests a form of cosmic evolution where universes that produce more black holes have more children, leading to a multiverse where the laws of physics are fine-tuned for black hole production. The false vacuum bubble hidden within a black hole is therefore the ultimate act of creation emerging from the ultimate act of destruction. A hidden structure that suggests our entire universe might itself be the offspring of a black hole in a long-forgotten parent cosmos. But if the false vacuum bubble suggests a black hole could birth an entirely new cosmos with different physical laws, our next hidden structure brings our focus back to the very fabric of our own universe, proposing that at the most fundamental level, reality is not smooth and continuous, but structured and discrete. Deep within the black hole's core, where gravity becomes unimaginably powerful, this fundamental architecture might manifest in its most extreme and beautiful form, a quantum gravity crystal. To grasp this concept, we need to challenge our most basic intuition about space and time. We naturally picture the universe as a continuous, seamless stage, an empty void that can be divided infinitely into smaller and smaller parts without any limit. But this intuitive picture likely breaks down at the tiniest possible scales. Theories of quantum gravity, most notably loop quantum gravity, propose that space-time itself has a discrete, granular structure. Imagine the universe is not an infinitely divisible ocean, but is instead more like a vast, cosmic piece of fabric. This fabric isn't woven from infinitely thin thread. It is woven from individual, fundamental threads, tiny, indivisible loops of space. The smallest possible unit of this fabric, the thread itself, is defined by the Planck length, a distance so incredibly small that it is a millionth of a billionth of a billionth of a billionth of a centimeter. You cannot have half a unit of this space. It is the pixel of reality, the absolute smallest possible size anything can be. Now, subject this granular fabric of spacetime to the most extreme pressure imaginable, the gravitational collapse at the heart of a black hole. In the classical view, this collapse continues unchecked, squeezing matter and space into an infinitely small point. But if space is made of discrete units, this infinite compression becomes impossible. You cannot squeeze something into a volume smaller than the size of a single pixel. Instead of collapsing to a dimensionless singularity, the matter and energy inside the black hole would be compressed to this ultimate density limit, where the repulsive force of quantum gravity, the inherent pressure of this granular structure, kicks in with unimaginable strength. At this point, the granular spacetime itself is forced to arrange into a highly ordered, rigid structure, a quantum gravity crystal. This wouldn't be a crystal made of atoms, but a crystal made of space and time itself, a literal lattice of reality with a precise, geometric arrangement of its fundamental units. This crystal core would have astounding properties. It could vibrate or resonate at specific frequencies, much like a struck tuning fork. These vibrations wouldn't produce sound, but ripples in the very fabric of gravity itself, gravitational waves with a distinct, high-frequency signature that, if we could ever detect them, would be the smoking gun for this theory. This offers a breathtaking vision of unification. The chaotic, force-driven world of quantum mechanics, with its probabilities and particles, finds common ground with the smooth, geometric world of general relativity in this ordered crystalline structure. The crystal is the meeting point, the physical manifestation of quantum gravity, showing that the universe at its heart is not a formless chaos but possesses a deep, hidden order. It transforms the center of a black hole from a place where physics dies into a place where the most fundamental laws of physics are written into the very lattice of space-time, a silent, vibrating heart of perfect geometric precision, beating within the ultimate darkness. Yet as we contemplate the profound implications of a quantum gravity crystal, we are drawn to another theoretical possibility that could dwell within these cosmic crucibles. A particle so elusive it has never been seen, yet whose existence could unlock the deepest secrets of the universe's forces. This brings us to a hidden structure that connects the immense scales of astrophysics to the smallest scales of particle theory, the magnetic monopole core. To understand why this is so revolutionary, we must first grasp a fundamental asymmetry in our everyday experience of magnetism. Every magnet we have ever encountered, from a simple refrigerator magnet to the entire Earth itself, has two poles, a north and a south. If you break a bar magnet in half, you don't get an isolated north and an isolated south. You get two smaller magnets, each with its own pair of poles. This duality is baked into the equations of classical electromagnetism. However, many of the most ambitious theories in physics, known as grand unified theories or GUTs, tell a different story. These theories aim to describe how the four fundamental forces of nature electromagnetism, the strong nuclear force, the weak nuclear force, and gravity, were once a single, unified force in the extreme heat of the Big Bang. A critical prediction of many of these models is that as the universe cooled and this unified force split apart, it should have created exotic relics, particles that possess only a single magnetic pole. These are magnetic monopoles, hypothetical particles that are either a pure north or a pure south, a fundamental magnetic charge. The problem is, despite decades of searching, no one has ever definitively found one. So where did they all go? One compelling answer is that they were drawn into the most powerful gravitational sinks in the universe, black holes. The early cosmos would have been flooded with these primordial monopoles. Their immense mass and unique interactions would have made them highly susceptible to gravitational pull, causing them to spiral inward and accumulate at the centers of the first black holes. There, shielded from our view behind the event horizon, they could have collected into a massive, stable core, a dense ball of pure magnetic charge sitting at the heart of the darkness. This isn't just a theoretical curiosity. Such a core would have dramatic, observable consequences for how a black hole behaves. The presence of a massive monopole core would generate astoundingly powerful magnetic fields, orders of magnitude stronger than anything we see around typical black holes. These fields would be the ultimate cosmic engines, capable of twisting and accelerating charged particles to nearly the speed of light. This provides a potential explanation for one of the most spectacular phenomena in the universe: the colossal jets of matter and energy that erupt from the poles of supermassive black holes in active galactic nuclei. These jets can stretch for millions of light years, shining with the brightness of 1,000 galaxies. The exact mechanism that launches and collimates these jets into such narrow, focused beams has long been a puzzle. A magnetic monopole core could be the answer. Its immense, organized magnetic field could act like a cosmic railgun, channeling and accelerating infalling plasma into those incredibly powerful and precise jets. The dynamics of this monopole core, whether it's a stable, singular mass or a dynamic, swirling fluid of magnetic charge, would directly dictate the power and behavior of these high-energy emissions, making black holes not just gravitational powerhouses, but the most powerful magnetic engines in the cosmos. The implications of this reach far beyond astrophysics and into the very heart of theoretical particle physics. The confirmed existence of a magnetic monopole would be a monumental discovery, providing direct evidence for grand unified theories and offering a glimpse into the universe's condition mere moments after the Big Bang. Finding one in a lab on Earth has proven incredibly difficult, as they are predicted to be incredibly massive and rare in our local region of space. But if they are concentrated inside black holes, then these cosmic giants become the ultimate natural laboratories. By studying the magnetic fields and jet activity of black holes, we might be indirectly studying the properties of monopoles themselves, testing our most profound theories of unification by observing their effects on a galactic scale. A hidden monopole core transforms a black hole from a simple consumer of matter into a vault guarding one of the universe's most sought-after relics, a place where the dream of a unified theory of physics is literally locked away, waiting for us to decipher its magnetic signature. But if the magnetic monopole core suggests a hidden engine of immense magnetic power, our next structure reveals an even more fundamental process working within the black hole, one that seals its ultimate fate not with a cataclysm, but with a slow, quiet whisper. This concept transforms our view of black holes from eternal monuments of gravity into transient quantum entities, and at its heart is a mechanism of breathtaking subtlety: the Hawking radiation engine. For centuries, black holes were thought to be the universe's ultimate dead ends, capturing everything that crossed their path and growing ever larger for all eternity. This changed in 1974 when Stephen Hawking performed a staggering feat of theoretical physics. By applying the rules of quantum mechanics to the curved spacetime around a black hole, he made a shocking prediction: black holes are not black at all. They should glow with a faint thermal radiation, and in doing so, they slowly lose mass and energy. This phenomenon, now known as Hawking radiation, implies that even the mightiest black hole has a finite lifespan, destined to eventually evaporate into nothingness over unimaginable timescales. But how does this work? The process begins not deep within the interior, but right at the precipice of the event horizon, in the seething quantum foam of empty space. According to quantum theory, the vacuum is not truly empty. It is a vibrant sea of virtual particle pairs constantly blinking in and out of existence. These pairs consist of a particle and its antiparticle, and they normally annihilate each other almost instantly, returning the energy they borrowed from the universe. However, if this fleeting creation happens right at the edge of a black hole's event horizon, the intense gravitational field can tear the pair apart before they can reunite. In this cosmic robbery, one particle falls into the black hole, while the other escapes into space, carrying away energy. To an outside observer, this escaping particle is the Hawking radiation. But here's the incredible twist. The particle that fell in doesn't just add energy, it has negative energy relative to the outside universe. This means that by accepting this negative energy particle, the black hole itself loses a tiny amount of mass. It's a slow, relentless leak that, over trillions upon trillions of years, will cause the entire black hole to evaporate. This process suggests that the black hole's interior houses a sophisticated radiation engine, a dynamic structure that governs this quantum theft. The infalling negative energy particles don't just vanish. They must be integrated into the black hole's overall energy budget. This could create internal feedback loops and zones of exotic energy density deep within. As the black hole shrinks, the temperature of the Hawking radiation it emits increases, and this engine would have to adapt, potentially becoming more efficient and violent in its final moments. The final stage of evaporation is not fully understood, but it might involve a runaway feedback effect where the remaining mass is converted into a final burst of high-energy particles. A quiet pop at the end of the universe signaling the departure of a cosmic giant. The existence of this internal engine completely revolutionizes the black hole's life story. It is not a static pit but a dynamic, evolving quantum system. It has a birth in the collapse of a star, a long life of accretion and growth, and eventually a death through this slow, quantum mechanical evaporation. The Hawking radiation engine is the hidden mechanism that powers this life cycle, a constant, faint hum of quantum activity that ensures nothing in the universe, not even a black hole, lasts forever. It is the ultimate irony. The darkest objects in the cosmos are perpetually glowing, their hidden hearts engaged in a delicate quantum dance that ensures their eventual return to the void from which they came. But what if the slow evaporation of Hawking radiation isn't the only way to escape a black hole's grasp? What if, instead of being slowly radiated away as particles, information and matter could traverse the interior via a secret cosmic shortcut? This brings us to a concept that has captivated both physicists and science fiction fans for nearly a century: the idea that a black hole might not be a pit, but a portal. We are now peering into the 23rd hidden structure, a theoretical passage that reimagines the very nature of these cosmic objects, the wormhole throat. The story begins with Albert Einstein and his colleague Nathan Rosen. In 1935, while working on the implications of general relativity, they discovered something remarkable within the mathematics. The equations that described a simple, non-rotating black hole, a Schwarzschild black hole, also contained a bridge to another, separate region of spacetime. This Einstein-Rosen bridge was the first theoretical glimpse of a wormhole. It wasn't a tunnel you could travel through. It was a mathematical connection, a shortcut linking two distant points or even two different universes. In this model, the black hole's interior would not contain a crushing singularity. Instead, it would house this bridge's narrowest point, the throat. Imagine an hourglass with two vast bulbs connected by a constricted neck. The throat is that narrow neck, the crucial passageway that connects the entrance to the exit. If a black hole is one bulb of the hourglass, the wormhole throat is the corridor leading to the other side. The classical Einstein-Rosen bridge, however, presented a colossal problem for any would-be adventurer: stability. The mathematics showed that this throat would be catastrophically unstable. The moment even a single particle of matter or a flicker of energy tried to pass through it, the gravitational forces would cause the tunnel to snap shut instantaneously, collapsing into a traditional singularity and crushing anything inside. This seemed to relegate wormholes to the realm of mathematical curiosities, impossible structures that could never exist in the real universe. But the dream of a traversable wormhole refused to die. The key to propping it open, theorists proposed, was something truly exotic: matter with negative energy density. This isn't antimatter, which has positive energy and would be gravitationally attractive. Negative energy matter, often called exotic matter, would possess a kind of repulsive gravity, a negative pressure that could theoretically push against the walls of the wormhole throat and prevent its catastrophic collapse. While this sounds like pure fantasy, tiny amounts of negative energy density have been indirectly observed in quantum effects like the Casimir effect, where two metal plates in a vacuum experience a slight attractive force due to the negative energy of the virtual particles between them. If such exotic matter could be harnessed and concentrated, it might be the structural reinforcement needed to stabilize a wormhole throat, transforming it from a mathematical possibility into a potential cosmic transit system. The implications of a stable wormhole throat are, of course, the stuff of legend. It would revolutionize our understanding of the cosmos, offering a means for instantaneous travel across astronomical distances. A journey that would take a conventional spacecraft tens of thousands of years could become a mere stroll through a tunnel. But the possibilities are even wilder than simple space travel. The mathematics of general relativity show that wormholes could also be time machines, connecting not just different places, but different times. The entrance and exit of the wormhole could experience time at different rates due to effects like time dilation, potentially allowing for travel into the past or future. This immediately raises the specter of infamous paradoxes, like going back in time and preventing your own birth. Many physicists, including Stephen Hawking with his chronology protection conjecture, believe that quantum effects would always conspire to destroy such a wormhole before it could be used as a time machine, preserving the linear flow of cause and effect that defines our reality. So, while the wormhole throat remains one of the most speculative structures on our list, its power lies in its ability to expand our imagination. It challenges the grim finality of the classical black hole model and offers a vision of the universe that is deeply interconnected, woven through with hidden passageways and shortcuts. It suggests that the interior of a black hole might not be a crushing void, but the vestibule to an incredible journey, a corridor to other stars, other universes, or other times, waiting silently in the heart of darkness for us to one day learn how to open the door. Yet even as we consider the profound implications of a wormhole throat, a gateway to other realms, we must also listen for the subtle vibrations that might reveal the black hole's true nature. Imagine the event horizon not as a silent, smooth boundary, but as a resonant shell, a cosmic drumhead that rings with the quantum whispers of the void. This brings us to a hidden structure that offers perhaps our first tangible chance to peer beyond the veil, a structure that turns the black hole into a celestial instrument, the quantum echo chamber. The concept emerges from a simple but powerful question. If a black hole isn't the perfect, featureless void described by classical general relativity, how could we possibly tell? The answer might lie in the way it vibrates. When two black holes collide, they create some of the most powerful events in the universe, sending ripples through the fabric of spacetime known as gravitational waves. These waves have been detected by observatories like LIGO and Virgo, and their main signal is a characteristic chirp, a rising frequency and amplitude as the black holes spiral inward and merge, followed by a ringdown, a fading series of oscillations as the new, single black hole settles into a stable state. According to Einstein's theory, this ring-down should be clean and smooth, like the pure tone of a perfectly struck bell, decaying away into silence as the black hole becomes quiet and featureless. But if the event horizon is not a perfect membrane, if it has any quantum structure, be it a fuzzy, stringy surface, a firewall, or a quantum gravitational barrier, then that perfect ring-down might be followed by something else. The gravitational waves could bounce against this quantum structure, creating a faint, repeating signal, an echo. Think of it like shouting into a deep, complex cavern. You hear your initial shout, and then a moment later, you hear a faint, distorted repetition of the sound as it reflects off the walls and formations deep inside. A quantum echo chamber within a black hole would work on a similar principle, but with space-time itself doing the vibrating. These echoes would not be random noise. They would carry a specific signature, a fingerprint of the hidden architecture near or just inside the event horizon, revealing details about its quantum nature that are otherwise completely invisible to us. This isn't just a theoretical fantasy. In recent years, some astronomers analyzing the gravitational wave data from the first black hole mergers have reported tantalizing, albeit controversial, hints of exactly these kinds of echo signals following the main ring-down. The statistical significance is still low, and the findings are hotly debated within the scientific community, but the very possibility has electrified the field. It represents a potential observational window into quantum gravity, a way to test these wild theoretical ideas with real data from the cosmos. The properties of the echoes, their timing, their decay rate, their frequency, would act as a diagnostic tool. For instance, echoes that return very quickly might suggest a firewall or a quantum structure very close to the event horizon. Echoes that take longer to return could indicate a deeper internal structure, like a wormhole throat or a Planck star core, creating a more complex internal geometry for the waves to traverse. A confirmed detection would be nothing short of a revolution. It would provide the first direct evidence that black holes are not the simple objects described by classical physics, but are instead governed by the strange rules of quantum mechanics all the way down. It would allow us to discriminate between competing theories. Does the data better support the fuzzball model of string theory, or the quantum loop gravity of a Planck star? The unique echo signature could tell us. The quantum echo chamber transforms the black hole from an inscrutable mystery into a cosmic broadcaster, its hidden vibrations echoing out across the universe, subtly encoding the secrets of its interior architecture for anyone with the sensitive enough instruments and the cleverness to listen. For decades, the reigning dogma in black hole physics has been the elegant, if sterile, no-hair theorem. This principle, heavily influenced by the work of John Wheeler, declared that black holes are the simplest objects in the universe. No matter how complex the star that formed it or what exotic objects later fell in, a black hole in equilibrium could be completely described by just three numbers: its mass, its electric charge, and its angular momentum or spin. Everything else, every detail, every bit of information about what made it is irretrievably lost behind the event horizon, erased forever. A black hole, in this view, has no personality, no history, no distinguishing features. It is a cosmic bald head, utterly simple and forever anonymous. But what if this theorem, for all its mathematical beauty, is wrong? What if black holes are not so forgetful? This brings us to our 25th and final hidden structure, a concept that proposes black holes are not bald at all, but are in fact covered in hair, a subtle, complex structure that records their unique and personal history. The term hair is a wonderfully evocative metaphor for these proposed additional properties that could adorn a black hole, making each one as unique as a fingerprint. This isn't hair made of keratin, of course, but hair made of incredibly subtle physical fields or structures that cling to the event horizon or permeate the space just around it. This could take the form of unique configurations of quantum fields that refuse to be swallowed, lingering just outside the point of no return and subtly altering the gravitational field. In some theories involving extra dimensions, like string theory, this hair could be manifestations of those higher dimensions imprinting themselves on our three-dimensional view of the black hole. Other proposals suggest that certain types of exotic matter or energy could create these permanent markers. The key idea is that this hair provides a way to store information about what fell into the black hole, not within a hidden interior, but right there on its surface, encoded in the intricate details of how these fields are arranged. It's as if every book consumed by the black hole's library has its title and author etched faintly onto the library's outer wall. Internally, this hairy identity would manifest in fascinating ways. Instead of a featureless descent into a singularity, the interior could be structured by complex patterns of energy, density, and pressure, shaped by the specific hair the black hole possesses. The distribution of matter and the very curvature of spacetime inside could be uniquely tailored, a direct reflection of the information stored on the horizon. A black hole that formed from the collapse of a single star might have a different internal energy landscape than one that grew by devouring countless planets and asteroids. The hair dictates the internal architecture, weaving a hidden tapestry of data into the fabric of the black hole itself. This challenges the very foundation of the no-hair theorem, proposing a universe where black holes are not identical clones but individuals, each with a rich internal identity and a story to tell about its past. The implications of hairy black holes are profound, offering a potential and elegant resolution to the infamous information paradox. If information about infalling matter is not destroyed, but is instead preserved in the intricate details of this horizon hair, then the sacred principle of quantum mechanics, that information cannot be destroyed, is upheld. When Stephen Hawking discovered that black holes evaporate through radiation, he initially thought this process would destroy information, as the radiation seemed purely random and thermal. But if a black hole is hairy, then the Hawking radiation it emits can be subtly influenced by this hair. The radiation wouldn't be random. It would carry the faint, encoded signature of the information stored on the horizon, slowly and faithfully leaking the black hole's secrets back out into the universe as it evaporates. The black hole's hair becomes the key that unlocks the data, ensuring that the universe never truly forgets. This concept represents a magnificent synthesis, a weaving together of the principles of gravity and quantum theory in a deeply personal way. It suggests that the most massive and destructive objects in the cosmos are also intricate repositories of information, their identities shaped by their history. The search for evidence of this hair is now a frontier of observational astronomy. By meticulously studying the gravitational waves produced when black holes merge, scientists are looking for tiny deviations from the predictions of the no-hair theorem, subtle ripples in the signal that could be the fingerprint of hairy structure. Finding such evidence would be a monumental shift, transforming our understanding of black holes from simple gravitational pits into complex, dynamic entities, each one a unique and detailed chronicle of everything it has ever absorbed. As we stand back from this breathtaking tour of 25 hidden structures, from the pulsating heart of a Planck star to the informational tapestry of a holographic horizon, it's natural to feel a sense of overwhelming complexity, even contradiction. How can a black hole simultaneously be a fuzzy ball of strings, a tunnel to another universe, and a two-dimensional hologram? The sheer diversity of these theories might seem like a sign of confusion, a cacophony of ideas where physicists can't agree on anything. But in reality, this vibrant theoretical ecosystem is not a weakness. It is the greatest strength of the scientific process, a sign of a field that is vibrantly alive and grappling with a problem of profound depth. Each of these models, for all their apparent differences, is united by a single, powerful mission: to resolve the fundamental paradoxes that arise when the two pillars of modern physics, the cosmic scale rules of general relativity and the atomic scale rules of quantum mechanics, collide in the most extreme environment imaginable. This shared goal reveals a deeper truth about the nature of black holes themselves. The classical image of a simple, empty void warping down to a silent singularity is not so much wrong as it is incomplete. It is a magnificent and accurate description for an outside observer, but it utterly fails when pushed to its logical extreme at the center. The proliferation of these alternative structures is a direct consequence of taking quantum mechanics seriously. Whether it's the fuzzball storing information in its strings, the firewall protecting quantum entanglement, or the white hole ensuring matter isn't destroyed but relocated, each theory is an attempt to weave quantum principles into the gravitational fabric of spacetime. They are all saying, in their own unique language, that the universe cannot tolerate infinities and cannot abide by the loss of information. The laws of physics, they insist, must remain consistent even at the edge of the abyss. So while a Planck star and a Gravistar propose very different mechanisms to avoid a singularity, one through quantum bounce, the other through dark energy pressure, they are both answering the same clarion call: the infinite must be made finite. This beautiful tension between competing ideas is not a stalemate. It is the engine of scientific discovery. The fierce debate between proponents of firewalls and fuzzballs, for example, forces each camp to sharpen their mathematics and seek out potential flaws, ultimately leading to more robust and refined theories. The wild speculation of wormhole throats and white hole fountains, while currently beyond our observational reach, expands the horizon of what might be possible within the laws of physics, challenging our imagination and preventing intellectual stagnation. This theoretical diversity is a necessary and productive phase, much like the early days of quantum mechanics, when competing interpretations vied for dominance. From that chaos emerged a deeper, more powerful understanding of the subatomic world. The same process is now unfolding with black holes. We are in the midst of a great synthesis, where these disparate threads are slowly being woven together. The holographic principle, for instance, provides a powerful framework that can accommodate several of these ideas, suggesting that the interior structures we've imagined might be different perspectives or approximations of a deeper, underlying reality where information is paramount. What emerges from this synthesis is a radical new portrait of a black hole. It is no longer a passive, simplistic pit, but a dynamic and incredibly complex entity. It is a quantum computer scrambling information, a gravitational engine extracting energy from its spin, a potential gateway to other realities, and a cosmic library encoding its history on its surface. It might be all these things at once, with different theories describing different aspects of its multifaceted nature. This journey through 25 hidden structures doesn't provide a single, easy answer. Instead, it provides something far more valuable: a glimpse into the future of physics itself, a future where gravity and quantum mechanics are not at war, but are finally understood as two expressions of a single, elegant, and unified truth. Our journey through these 25 hidden structures reveals a cosmos far more wondrous and intricate than the simple, dark voids of classical theory. We began with the unsettling singularity, a mathematical warning sign that our understanding was incomplete, and we have ventured through a spectacular landscape of alternatives, each one a testament to human ingenuity and the relentless pursuit of knowledge. From the pulsating quantum bounce of a Planck star to the holographic date, a screen of the event horizon, from the destructive fury of a firewall to the creative potential of a white hole fountain, these theories do more than just propose new interiors for black holes. They fundamentally challenge our conceptions of reality itself, forcing us to ask whether space and time are fundamental or emergent, whether information is a physical substance, and whether the universe we see is the only one that exists. This is not merely academic speculation. The struggle to understand what happens inside a black hole is the same struggle to unify the two great pillars of 20th century physics: general relativity and quantum mechanics. The black hole is the ultimate testing ground, the place where both theories are pushed to their absolute limits, and where their contradictions become impossible to ignore. The incredible diversity of ideas we've explored, the fuzzballs, the gravastars, the vortex lattices, is not a sign of failure, but a sign of a field in its most productive and creative phase. Each model is a different angle of attack on the same profound problem, a different language trying to describe the indescribable. What emerges is a new picture of black holes not as cosmic dead ends, but as dynamic, evolving entities. They are quantum computers, gravitational engines, potential universes in embryo, and the most secure libraries in existence. They are not simple. They are perhaps the most complex objects in the entire universe. This exploration reminds us that the universe is under no obligation to conform to our intuition. The truths hidden in the heart of darkness are strange, counterintuitive, and often unbelievable, yet they are beckoning us to discover them. The fact that we can use mathematics and observation to peer into such an inaccessible realm and develop such breathtakingly sophisticated theories is a glorious achievement for our species. It speaks to a deep and powerful truth, that the human mind, armed with curiosity and rigor, can begin to comprehend the cosmos on its most fundamental level. The study of black holes is more than astronomy. It is a philosophical journey into the nature of existence, causality, and the very laws that govern reality. As we continue to develop new technologies like ever more sensitive gravitational wave detectors and space-based telescopes, we move from pure theory toward the possibility of actual observation. The faint whispers of quantum echoes in gravitational wave data, or the specific signatures of a particular magnetic field structure around a supermassive black hole, could one day provide the evidence we need to distinguish between these dazzling ideas. The conversation is ongoing, and you are living in the time when it is happening. This is not settled science. This is the cutting edge, a thrilling frontier where the next great discovery could come at any moment. So keep asking questions, stay curious about the universe's deepest mysteries, and always remember to look up at the night sky with a sense of wonder. The greatest secrets are still waiting